Right now, the global energy industry is quietly buying up the world's computing power. French energy giant Total Energies recently invested over 100 million euros in a single piece of hardware, a next-generation supercomputer called Pangea 5. The company is building its own dedicated infrastructure to multiply its computing power six-fold. They need that extreme processing capacity to run massive climate models and process the complex seismic data required for energy exploration. But hardware of this size exposes a persistent challenge in modern computing. Engineers equipped Pangea 5 with specialized processors optimized for parallel computations, achieving a 40% reduction in energy usage at equivalent performance levels. Yet even with that efficiency, the system still generates a staggering amount of heat. This heat map data visualization illustrates the scale of that thermal output. The residual heat radiating from Pangea 5's processors is so massive that it is actively captured and funneled outward to warm a surrounding facility that houses more than 2,500 people. Pangea 5 highlights a growing friction in high-performance computing. While we can build faster machines, their rising energy appetite and thermal output are forcing energy giants to spend millions just to manage the byproduct of their own calculations. That thermal limit isn't isolated to massive corporate supercomputers. The exact same energy crisis is happening right now in the technology sitting in your pocket. Mobile software demands are skyrocketing. Samsung's One UI 8.5 update introduces agentic AI. Instead of just reacting to individual commands, this intelligent assistant uses large language models to autonomously decide on and execute complex multi-step actions on your behalf. Hardware demands are compounding at the exact same time. Samsung is replacing external biometric wearables with sensor OLED displays, forcing the phone itself to track your vital signs continuously. This animated diagram breaks down the mechanics. The display structure contains embedded organic photodiodes. When you place a finger on the screen, these sensors use the panel's own emitted green light to penetrate your skin and read blood flow patterns directly. When you cram continuous medical monitoring and autonomous AI into a pocket-sized sheet of glass, you create an immediate energy bottleneck. Traditional silicon chips simply drain too much battery and generate too much heat to keep up. To break through this energy wall, engineers are abandoning the traditional silicon blueprint entirely. They are redesigning hardware to copy the most efficient computer in the known universe, biological nature. Modern computers suffer from the von Neumann bottleneck. Data traveling between separate memory and processors wastes enormous energy. Cambridge researchers eliminated this traffic using a memistor. As the blocks merge, it mimics biological neurons, storing and processing data in the exact same physical space. By modifying the crystalline structure of hafnium oxide, the Cambridge team stabilized these memistors to operate on incredibly low switching currents. In active AI workloads, this single architectural change cuts energy consumption by up to 70%. Solving the artificial intelligence energy crisis does not require building bigger data centers. It requires us to redesign our physical hardware from the ground up so it behaves like biological tissue. If mimicking biology is the only way forward for hardware, it raises a question about software. What if an intelligent machine didn't need a centralized processor or complex code at all? Researchers at Leiden University in the Netherlands have 3D printed a series of microbots measuring just a few tens of micrometers long. They are completely invisible to the naked eye, far smaller than the width of a human hair. Yet, as they move through these fluid-filled channels, these structures can swim, navigate narrow spaces, and actively avoid obstacles. They do this with zero onboard software, zero sensory electronics, and zero central controllers. The robots operate on a principle called morphological computation. In an alternating electric field, parts of the robot's flexible body contract and expand. The physical shape reacting to the environment is the intelligence, exactly how basic biological organisms navigate. A centralized brain is not a requirement for intelligence. Nature proves that physical adaptive design can entirely replace hundreds of lines of complex computational code. So, if copying biological shapes and mimicking biological hardware solves our hardest engineering problems, why stop at mimicking? Why not compute using the real thing?
Scientists at Princeton University have created the 3D Mind. It is a functional, hybrid biocomputing platform that operates as part electronic machine and part living organism. The device consists of approximately 70,000 living biological neurons grown from stem cells. These cells actively grow through and wrap around a flexible three-dimensional electronic scaffold, forming a stable connection where tissue and electronic hardware can directly communicate. This bar chart displays the strict mathematical logic driving this biointegration. The massive column illustrates the megawatts of electricity required by modern AI. Down here, the almost invisible speck shows the biological human brain, which performs similar tasks using roughly 1/1,000,000th of that power. Because this platform utilizes living networks operating in a 3D architecture, it offers far richer connectivity than flat 2D cultures. This gives medical researchers a highly accurate biological environment where they can test neurological drugs directly on functional neural networks outside the human body. Platforms like 3D Mind represent a shift in how we define a machine. By integrating living tissue directly into hardware, researchers are starting to move past the binary of electronic tools versus biological entities. As we move toward 2030, the path to more powerful computing may no longer lead through bigger silicon chips. Success in the next generation of technology will likely depend on how well we can learn from and eventually integrate the extreme efficiency found in the raw building blocks.